Hi, Lisa. Could you hear me?
Hi, Johnny. How are you?
Hi. Good morning.
Morning.
Well, evening there. So how's your life? How's your summer so far? I know that Oregon summer is beautiful.
Yes, I'm in Oregon. This is where I am, this background. And I'm splitting my time between San Diego and here. And so I'm having a good time. I just went on a beautiful hike today, and I'm looking forward to this talk.
Okay.
How are
Sounds
you?
great.
Johnny, I haven't seen you in a long time.
Yeah, I haven't seen you for a while. I plan to go to AGU and hopefully visit Scripps probably next year at some point. Haven't seen a lot of people. Yeah, life is being good. On the one hand, I push for machine learning application in geochemistry, as you might see. And on the other hand, I have a baby. My baby is sleeping now. Actually, if she's awake, I want to bring her to the camera. Maybe, I think later, because you're talking about last one.
I might get interrupted by two grandchildren here too, but I told them that I was busy.
But I think it's okay. I mean, our previous speakers bring cats into their talk, wine. So it's okay. It's a little casual. I think the good aspect on Zoom talk is that, as I say, people could wear shorts and being more.
How old is your baby?
5 months old.
Oh, exciting! Very exciting.
Yeah, she's very cute.
I love babies.
Yeah, people all love that. Yes, it's a very good opportunity for me to do my self-reflection, because seeing her behavior and some of her physical and probably mental features, that's also a reflection of myself. So it's quite interesting to see myself, how I did grow up from my own perspective. It's easier to observe others than observe myself. So it's a pretty interesting experience to me. Yeah, I feel quite excited about that.
Yeah, it's exciting. Don't miss a minute.
Yeah, it's irreversible. Unlike geology experiments, a lot of experiments are irreversible. We could do it again, but for kids, we won't. So right. Okay. Right. Okay, could you try to share slides? Let's see how the slides goes.
Okay, I'll try to share my screen. And I'll start the slideshow. Can you see it?
Yes, I can see it. Okay. Could you turn next page? Let me see if there's any delay.
Okay, how's that?
I haven't seen the second page yet.
Okay, let me try. Okay.
Okay, before we start, yeah. Now turn. Okay, now it returns to the cover page. Okay.
Yeah. Okay.
Okay. That's okay. Yeah, interesting. A little bit trivia about Zoom. Actually, Zoom has 3 offices in China, but not 1 office located in Hangzhou. So most of the codes that we are using the Zoom, the product, let's say significant proportion of the codes are contributed by software engineers in Hangzhou. Actually, it used to be in an office, not too far away from my previous office. I mean, I have one office. I stayed in one campus for 3 years before our department moves to a new campus here, but in the same city. So there are a lot of Zoom engineers in the city. I happen to know some of them.
That's great. A wonderful product. It got us through COVID. It was without
beyond. Now it's post-COVID, but still useful.
What would you do without Zoom? Yeah.
Okay, Lisa. So before we formally kick off your talk, we would like to do a group picture. So could you stop sharing your screen and let everyone turn their video so that you can see their faces? So everyone, could you open your video? Yeah, and smile so that our speaker could see that she's not talking to robots, but to human sapiens here.
Real people. But there's 2 more pages of people. Wow, so many people.
Yeah, they are mostly undergrad students, but some of them are graduate students. And as you can see, some of the students, they are still in a field trip. Actually, I think, yeah, they're in different parts of the world for that field trip.
Okay, nice.
Yeah, so they all come to your talk. It's great to know geomagnetics. Yeah, so it's quite exciting to have this talk.
Mm-hmm. Okay, so
Okay. So everyone, I think you can turn your video off. I think that will guarantee better smooth experience when connecting to this talk. So feel free to turn off your video, and then Lisa, you could begin sharing your slides, and we are going to kick off the talk very soon.
okay. Sure. So are we back to where we were?
Yeah. Okay.
Okay.
Okay. Good morning, good afternoon, good evening. Welcome to the 自居尔的 webinar for the 海外名师大讲堂. Today is our great pleasure to have our speaker, Lisa Tauxe, speaking with us, talking about the magnetic field. So Lisa got her undergraduate degree at Yale, and then her PhD at Columbia, and then she spent many years at the Scripps Institution of Oceanography. And now she's splitting her time between Oregon and San Diego. And Lisa has won many awards. I won't list all of them. And one of them, she was elected to National Academy of Sciences. And Lisa is a very interesting person that I happen to know Lisa personally to a certain extent, especially by spending on Thanksgiving day partying Lisa Tauxe home. And that's a really great experience. And today we are going to see more of the geomagnetic field, which is one important research direction in geology, but I think in our School of Earth Sciences here, it is a little bit underrepresented. So I hope that this talk could not only let everyone knows a little bit about the geomagnetic field, but also if some of you are interested in that research direction, I highly encourage you to consider choosing that as your career. So with that, Lisa, I will give the rest to you. And our talk normally is split in 2 sections. So first section is about some basics. So feel free to go slow, and then people will ask them questions. Then we'll take a very short break. Then on the second part, we could talk about the research. So as I mentioned earlier, it's a little bit casual. So feel free to bring your cats, your babies, and your wine, probably.
Yeah.
Okay.
Okay. All right. Yeah, I don't have any cats, but I do have 2 babies, but I think they're gone. So we'll see. Before I start, so you'll just have to stop me when you want to ask a question, okay, Jenny? Because I can't see the chat or anything when I'm running the show.
Okay.
All right?
Okay. I'll keep an eye to the chat. And so for our participants today, if you have any question, feel free to type in the chat. I could help you to interrupt the speaker for that question. Okay, go ahead.
Okay, so thanks to you for inviting me. Thank you very much, Jenny. It's a pleasure to give a talk again. And I'd also like to thank my family, my husband Hubert, who helped with many field trips because he's an expert in volcanology, and my children have also picked up the habit of drilling rocks. That's my older son Daniel, who's the father of the 2 grandchildren I have, and my son Philip, who is goofing around. And then I have 2 new assistants here who are very eager to start helping me in the field. Also, my students who helped on this particular project that I'm going to talk about, Jeff Cromwell and Hannah Asafa, Brendan Siege, and my colleagues, Haggai Ron, who unfortunately passed away, my postdoc, Ron Shar, a friend, John Sinton, and a master's student, Nicole Behar, from Israel. And so what I'm going to talk about first is a little bit about the magnetic field, why we care, how do we study it, and some thoughts about what we can do next. So I want to mention that the first compasses were made during the Han Dynasty, and they could detect the field, and they were south pointing and not north pointing as our modern compasses are. And there's a replica that's been made of this lovely little spoon, which points south. Then the compass arrived in Europe in the 12th century, apparently, but really wasn't used extensively until the 15th century. So Gilbert, William Gilbert, in 1600 wrote a book called De Magneta, which is about magnets. And he looked at the magnetization of a magnetized sphere. He called it a terrella, which in Latin means a little earth. And he took nails, magnetized nails, and discovered that this terrella has, when you put a nail on at the poles, they point straight up. And when you put them on the equator, they are flat against the ball. And then he knew from seafarers, captains, and people who traveled that the magnetic field does the same thing. The Earth's magnetic field does the same thing. And he has this famous quote, "The Earth itself is a great magnet." So the next slide shows a simplified version of the magnetic field, where the blue lines are those that would be generated by a little bar magnet at the center of the Earth. And you can see that at the poles, the field is vertical, and at the equator, the field is horizontal. But the real field, the Earth's field, is much more complicated than that. It has not only this dip, this inclination, but it varies in strength over the surface of the Earth, and has many features that are added by not just a bar magnet at the center of the Earth, but other terms. And so we have, first of all, the orientation of the magnetic field with respect to the North Pole, which is declination, and the dip of the field, which is called inclination, and the field strength. And I'm going to talk mostly about field strength in the rest of this talk, but it's important to understand that the field is complicated, more complicated than that of a simple bar magnet. And in fact, in China, there are records of the measurements of declination, which is the angle with respect to true north, through time. And you can see that starting around in 600 AD, there are measurements that were made in China and of the changing magnetic field. So Chinese scientists knew all about the magnetic field, that it pointed roughly north, and that it changes through time. This is something that the Europeans never figured out until after Gilbert in 1600. So things that we might want to know about the field are, where does the field come from? And we know that it's generated in the core, the Earth's core, through motions. It's iron, a liquid iron core. The center of the Earth, of course, is solid. But in the liquid iron core, there's many fluid motions, and that's what generates most of the Earth's magnetic field. Then how long has it existed? Well, that's still a contentious question. but most of us believe that it's been most of Earth's history. In fact, there isn't a time when you can't find a magnetic field. Of course, we don't have rocks that go all the way back to the beginning of the Earth, but whenever you have rocks, you have a magnetic field. So did the magnetic field play a role in allowing life on Earth? Some people think that because of this shielding, you see, this is a picture of the magnetic field done by one of my students who took my class. He was an artist. It's a beautiful picture, I think. And you know, you have, oops, what happened? Oh dear. All right, I'm gonna have to start this again. Okay, there it is. Can you see it, Johnny?
Yes, it looks good.
All right, so there's this shielding aspect of the magnetic field, which protects us from solar radiation and from magnetic storms and from cosmic radiation. And some people think that that's essential for protecting the surface of the Earth, the atmosphere, from being blown away like it is on Mars, and preserving, allowing life to develop on the Earth. That's the story we tell ourselves. I don't know whether that's true or not, but that's how we sell what we do. Okay, so then other questions come into play, and that is, what's the average strength of the field? And has it remained constant throughout the history of Earth? And the fact is that no, it changes a lot. And the average, I think, is about half of today's field. So when we talk about, is there a likelihood of a reversal of the field in the future? These are the kinds of things that you need to know about what the field is like over time. And how fast and how much can it vary? And the answer is it can change very rapidly. It's changing fast now. It's changed fast in the past. And it changes a lot, orders of magnitude of field strength throughout history. And finally, what can it tell us about the Earth's inside? Like, for example, was there an inner core or not? This is excuse me, what? Somebody said something and I didn't get that.
No, I think that's some random noise because someone hasn't muted their microphone. Yeah, go ahead.
So there's great debate now about when the Earth's inner core started to form and whether you can see it from the strength of the magnetic field changing through time and that kind of thing. And that's ongoing research, and I'm not going to talk about that today. So how do you study the Earth's magnetic field? We can do it in a lot of ways. The first way were direct observations, like the Chinese in the early first millennium, making measurements of the Earth's magnetic field. We make measurements now with satellites, ground-based observatories. This picture up here on the upper left is a picture of an observatory in Alaska with polar bears playing around outside. Ooh, I don't like polar bears, but and other human measurements, we've been measuring the field for quite a while. And so that's one way to study the field. Another way is to simulate it with numerical simulations, with what are called geodynamo simulations. And this picture, the second one down on the left, is an iconic, it was a cover of Nature magazine back in 1995. And it's a numerical computer generated simulation of the magnetic field. And that's another way to study the field, is just with very, very large, very, very fast computers. And people have tried to generate a self-sustaining magnetic field in the lab using liquid like sodium. And as far as I know, nobody has succeeded in actually making an Earth-like dynamo in the lab, although people have spent a lot of time trying to do that. Maybe Johnny, you know something more about that than I do, but then the way that I do it is through what's called, I call accidental records. So they're not planned. So for example, lava flows when they cool, and also pot ceramics. When you make a pot, you trap the magnetic field in those objects, and so you can then study lava flows or sediments or many natural geological materials, and you can get an idea of what the magnetic field was doing at the time. So I'm going to now talk about what you do with the direct observations. So here's a satellite that made a big news in the 1980s. It's called MagSat. It flew around and made a lot of measurements, and these measurements can be, along with the ground-based observatories, can be translated into a table of coefficients, which then from that table of coefficients called the International Geomagnetic Reference Field. Here's an example of one. Here, these are all the coefficients, L and M. And the first one is the magnetic dipole at the center of the Earth, aligned with the spin axis, and the other terms just get smaller and smaller and smaller. You can see as you go to higher and higher order of the things. And these numbers here, 1900, 1905, 1910, up to 2025 are years. So to understand what the field was like in 2020, all you need is this list of coefficients. And from that, you can calculate what the field vector was any place outside the core. So then you can draw a picture like this, which is generated from one of those maps. You can see the details of the magnetic flux coming out of the core. And that's one way to visualize that complicated list of numbers. And there are other ways of looking at the same information. For example, you can make maps of field strength over the surface of the Earth or on the core mantle boundary or wherever you want to. And so the upper right-hand picture is a picture of the field strength over the surface of the Earth. And you can see that from a simple dipole, you would have a big red dot at both poles and a blue belt around the center where the field is lowest at the equator and highest at the poles. It varies by a factor of 2 according to dipole formula, but you can see it's more complicated than that. And that's what I find interesting about the field, is that it isn't simple. And these pictures change through time. So this top one is a picture of the magnetic field today with these 2 hotspots, and then down on the South Pole, there's 2 very high field spots. And then around the equator, you can see it's quite variable. There's this thing called this South Atlantic anomaly, which is a region of anomalously low field strength, which comes and goes through time. So the idea is that you can make these maps through time, and then you get a picture of how the field changes. This one here is the same thing, only with the dip of the field, and you can see it goes from straight down up here somewhere, and now it's somewhere in Siberia where it's actually straight down. And down here in Antarctica, it's straight up. And then the inclination changes from straight up to horizontal to straight down as you go from the South Pole to the North Pole. So about those dynamo models, the simulations, these are pictures from that first paper, the iconic paper from 1995, when Blotzmeyer and Roberts got a three-dimensional self-consistent computer simulation of the geomagnetic field and how it reversed. And this was a very cool paper because you could see what happened when the field went from being pointing north to pointing south and the details of what happened inside. And so you can see that these models are just enticing, but how good are they? We don't know, because in fact, in order to make these models, you have to assume things, the computers are not big enough and not fast enough to simulate anything like the true Earth. For example, the numbers used for the viscosity of the core, outer core, instead of being close to water, are close to some asphalt or tar. So it's off by 10, 15 orders of magnitude. So these models, even the modern day ones, the ones today, which are much better than the ones 1995, are still not realistic. But people are arguing about how we can evaluate which ones are closer to the Earth and which ones are farther than the Earth. But my attention was grabbed by a recent model, which was put out by Lezin et al. This year. And they, in this paper, they had some diagrams and some predictions of magnetic field strength through time. So this is the intensity of the axial dipole. That's that first term of the reference field tables, and how it changes through some kind of time. There's a proxy for time on the x-axis and a proxy for the number one, the dipole field strength here, and it changes through time, which the Earth's field does. And then this is the present field of our Earth, the true Earth. And this is what I think is the average of the field through time here. So this model appears more realistic, and they've done a better job of mapping the data that they have into values that we can compare to things we measure on Earth. And what I found most fascinating about this paper was that they predict that when the field strength is very strong, up here, stronger than the average field, there's an asymmetry between the northern hemisphere and the southern hemisphere strength of the field. And the blue line is the northern hemisphere and the red line is the southern hemisphere. And this model predicts that there's this hemispheric asymmetry a little bit, it's stronger in the northern hemisphere and weaker in the southern hemisphere. But when the field strength is lower, like what I think is what is the average field strength for the Earth, there's no asymmetry. So this is a kind of prediction that maybe we can find whether it's borne out in the data from the Earth. So here is a model of the field variations over the last 10,000 years by the first author is Kathy Constable from Scripps, and it was published in 2016. If you take this is a series of those international geomagnetic reference field models, all those numbers, those lists of numbers, that goes back 10,000 years. And she did that by not just using people measurements, but I mean, human measurements, but also taking into account all of the kind of data that I generate and others in my field generate to make these maps going back 10,000 years. And if you average all of those coefficients and you make a plot of field strength over the surface of the Earth, please notice that that South Atlantic anomaly is smoothed out and really isn't there. But if you look at 65 degrees north, the average field strength is 65 microtesla. And if you look at 65 degrees south, the average field strength is 55 microtesla. So this shows that the average field strength is, it's high, it's very strong over the last 10,000 years compared to average. And that there is this, it seems to be that there is this asymmetry in the field that is predicted by, I mean, this paper was published in 2016 and the geodynamo modelers predicted it this year. So that's typical of those guys, that we find something and then they predict it, but that's not the way prediction is supposed to happen. But anyway, we can test their model by looking at data like this. This on the right hand is from taking all the paleomagnetic directional data for the last 5 million years, creating an average, time averaged field model. And then from that, you can predict intensities on the Earth, even though this is based entirely on directions. You can see that in this model, there is also a field asymmetry that appears to hemispheric asymmetry that appears here. But these data here for the last 5 million years are actually dominated by the last few million years. So did the field strength change over that time? And did the asymmetry disappear if you have more data? So just a temporary set of conclusions here. The average of these field time varying field models predicts long-term hemispheric asymmetry for a period of time where the field strength was quite strong. The time average field for the last 5 million years also predicts hemispheric asymmetry, and the numerical geodynamo models predict hemispheric asymmetry, but only for times of high axial dipole strength. So can we see changes in this over time? And that's what I want to talk about today. So how do we study the Earth's magnetic field in the past before people were going around measuring it? So we start by collecting igneous rocks, lava flows, for example, or cinder cones, or any kind of volcanic rock that cooled in the magnetic field. We can measure their magnetism in a lab. We can replace the original thermal remnants. It's called TRM, thermal remnant magnetization. We can replace that in the lab with a partial one in a stepwise fashion. And we assume, and we can also test that the strength of both of these different kinds of thermal remnances are linearly related to the applied field. We know it's not exactly linearly related from theory, but it is approximately linearly related to the field, at least in Earth field strengths most of the time. So we can then calculate the ancient magnetic field from the ratio of the original magnetization and the lab magnetization, knowing the lab field strength. So I say here's a picture of me doing field work in Antarctica with a helicopter that has a problem. And so It's how I say, what could go wrong with this very simple theory and idea? So I'm going to explain a few of the ways that this experiment can go wrong. By the way, that's funny because the hood is up, and if you ever drive a car and you see the hood up, that's not a good sign for the reliability of that vehicle. And this is a helicopter that's having a lot of trouble, and we almost had to walk back to our field base camp, which was down at the bottom of this hill in the middle of Antarctica. So that was not a good day. There's in a much warmer place, Hawaii, there was a place on the eastern edge of Hawaii. This is Big Island of Hawaii. It's got a lot of active volcanoes on it. And there was one that came out in 1960, which unfortunately in the last eruption, it got covered up. So nobody can go back there now, which is too bad. But we did manage to sample it. And actually a lot of people measured data from that same flow using very many different techniques. So we can find out whether they got the right answer or not. So here are the data from many, many studies on this same lava flow. One lava flow should give us one answer. Now, I just put here the range of the Earth's field today on the surface of the Earth. And this is this one lava flow, which should give us a very tight answer. And these are the data from published in the literature from this same lava flow. And you can see there is absolutely no reason at all why we should believe any of it, because it spans, it's more than the range of the Earth's field today over the entire surface of the Earth. So this is terrible. Very distressing. None of these papers seem to realize how bad they looked. And so I call this, you know, oh no, oh my goodness, this method doesn't work at all, which is depressing. So I thought about this a lot, me and my students, and we've come up with a different approach, and I call this the stepping stones to a different approach. So we start with the physical theory of how rocks get magnetized. And in order to do that, you have to stay with very fine-grained, rapidly cooled materials, because anything that's coarser grained does not conform to the simple physical theory that we have. And the 1960 flow was sampled not with the finest grained material, but in the center of the flow. And so now it doesn't surprise me that those data are so bad, because they haven't stuck with the physical theory. You use experimental methods that test the assumptions of the what you're trying to do. And you use data processing to find the best answers and the uncertainties. And then you ground truth the results on material with a known field strength, like the 1960 flow. And we knew what the field was when that lava flow came out, because of all of our international geomagnetic reference fields, which go back to 1900. And so 1960 is easy peasy. We just can calculate what the field was at that place at that time. And then we having done that, we apply it to older rocks, and we hope that it still works. So we've tried a lot of different rocks. We try lava flows. Here's my student sampling a lava flow in the Golan Heights of Israel, and they do not work for the reason that the grains are just too coarse. We've sampled cinder cones flow tops, which are quickly cooled. Cinder cones are these things that erupt and cool very quickly. The basal breccias of lava flows work very well. And also the margins of dikes chill very quickly. And so they have the right kind of grain sizes so that we can hope that the experiment will work. Then we apply an experiment, which we call the ISI method, which is first you measure the magnetism of the rock, as I said, then you heat the sample up to some temperature here called T1 and cool it in zero field. And then from theory, this is supposed to erase the magnetization with grain sizes that unblock and go random at T1. And then you repeat that same temperature, you cool it in a field, and then it replaces that these non-magnetic grains, and then you give it a new thermal remanence. And then you just keep going, and sometimes you repeat a lower temperature to check whether this is the same partial thermal remanence as this one that we gave originally. And if it isn't, well, that's bad. And then we repeat this experiment so that in this experiment we can test the assumptions of the method. Now we get plots like this one, where you plot the remaining magnetization at each step against the magnetization that was acquired at that same temperature. So each of these dots is, this is the original 0 temperature, and then at 150 degrees C up to the ultimate Curie temperature of 560 in this case degrees. And these are the dots for the magnetization, and these should fall along a straight line. This guy fails because one of our repeated lower temperature steps is completely different than the original one, and so that's bad. He fails. This sample, you can see I plot the magnetic direction during this experiment, and it should go on a straight line into the origin, and this one is quite curved, you can see. So there's actually 2 magnetization directions in this rock, and so that fails because it's not a single component. Maybe it got reheated, and you don't want to mix the field strength of this one with the field strength of this one, so that fails. Then this experiment was poorly designed. There's not enough data points in there, so bad. This is not a line, as you can see. This is a curve, and so this fails because it's not a straight line. I mean, what's the field strength? You take the ratio, you take the slope of this line and multiply it by the lab field. That's how you get the ancient field strength. And there's 2 different ones. Which one's the right one? I don't know. Is it this one, that one? I don't know. So he fails. And this one is all zigzaggy, and so that one fails. And this guy passes all our tests, and we love him, and that's a good result. And then you hope that you can get a few, 3 or 4, or at least specimens from that lava flow, and that gives you that answer. And then when we apply this method to our friend 1960 flow, we see that these are the answers that we got, and they're very tightly constrained. The expected direction from the field reference field model is this dashed line, and so we think we did it. Yay, we can do this. So the problem with this approach is that basically the data have to be perfect. So most data that have ever been produced in this fashion are thrown out. And that's very sad. And so we've developed a new approach that's not exactly what I just laid out. It's a bit of a risk. It makes the empirical assumption that curved plots are linearly biased with respect to the true value. And we have a Bayesian method of getting an intensity estimate with 95% credibility intervals. And we have tested this on things like the 1960 flow, and we find that it works really well, which is surprising. But hey, so here's an example of one. This is one of the data, one of the examples of a perfect specimen, but there were many other specimens from this same lava flow. And this is curvature. It's a proxy for curvature of the ARI plot. This one is perfectly straight. You can see this guy is quite curved. So some of these are more curved, and these are curved up, curved down, and it does form a pretty straight line, so that we feel justified in our assumption that curvature and field strength are related, but it's not, you cannot use a sample like this alone to calculate the field strength. You need an ensemble of data points, and you can estimate what the field strength was, and you have 95% credibility intervals. So this allows us to be a lot less picky about our data, and so we can have more answers, but it requires a lot of data. So that's the idea. So BICEP, this is a method we call bias corrected estimation protocol. And that's BICEP, which, if you know that, that means that's your arm muscle. So BICEP gives us more results, and it gives us the right answer on things that we know the answer for. So we're optimistic that we can actually use this method. And so now we think we know how to do the experiment. We've been to a few places, and we take the exact same approach, sample the same kinds of materials, use the same laboratory experiment, and now we can look at the results. So I'm going to show you data from Hawaii, from Iceland, from Israel, and from Antarctica, and we'll talk about what those data mean. So here are the data from the 4 different places that we've done in exactly the same way. So these are the data from Antarctica. One of these is one from that sad helicopter picture. And so this, we've converted, instead of field strength measured at the place, we've converted these data into what's called a virtual axial dipole moment, which is basically converting it to that first term in the geomagnetic field expansion. And that way we can compare data from around the globe, because field strength, as I mentioned, varies as a function of latitude, but we don't care about that. What we care about is what is the axial dipole moment. So these are equivalent, these were all calculated in exactly the way that I just described. This is from a paper that was published in 2021 by Hannah Asafa, and so the average of all of her data from Antarctica is around 40 zeta amp meters squared. Now the present field is 80 zeta amp meters squared. So her data are consistent with this long-term average that I talked about. And then these are the data from Hawaii, but these only span the last 300,000 years. They are quite strong. The data from Israel are, again, stronger than this. These are all these are all Pleistocene data, but the problem with the Hawaiian data set is that it only goes back 300,000 years and not 2 million like the other records. This one from Israel, you can see that the field strength is higher on average. All these Northern Hemisphere data are higher than the Southern Hemisphere data. And the other thing that's interesting is that the poles are depressed. So these are the data from Iceland, and they're lower than elsewhere in the Northern Hemisphere. But on average, the Northern Hemisphere is stronger than the Southern Hemisphere. And that is what was predicted by, after this paper was published, I should say, by the numerical field models. And here are the same data plotted as cumulative distribution functions. So CDFs, and these are the data from Antarctica. These are the data from Iceland. These are the data from Northern Israel, and these are the data from the Hawaii drill core. But like I said, and then there's a database full of data that have been published by a lot of other people, because these are only 4 studies done in exactly the same way. But there's a database of intensity data that have been published by everybody over the history of paleomagnetism. And so they were not done in the same way that I just described. They were done however that particular lab wanted to do it. So it's very difficult to compare those data with our data. However, if you make certain filters, you can maybe get close. So here are the data from the database. These colored dots are the ones.
Yeah,
from...
Lisa.
Yes,
Lisa.
sir.
So there's one question from undergraduate. So could you move to one page earlier? Yeah.
This...
Okay. I think this slide is perfect for question. So student asking a basic question about that, how to determine the geochronology according to the variation of the geomagnetic field.
Oh, that's another whole study, and that's a very interesting question and a very interesting thing to study. So what you can do, and I'm just about to publish a paper on this topic, what you can do is you can take those time varying field models, like from Constable et al., and there's others, and you can then assume that you know what the field was, and then if you find that particular direction at that place, then you would say, well, that happened at that time. So you can use the magnetic field to date things. This is something that is, in my opinion, very dangerous, but it's been done many times. This paper that I just submitted asked a simpler question, and that is, in Mesopotamia, you have a number of buildings that were built out of mud bricks that were fired. And then same thing in Israel. And so there was a question about whether this one particular building called the Ishtar Gate, which was built by Nebuchadnezzar in 500 BC or so, whether it was built at the same time or right after Nebuchadnezzar had destroyed Jerusalem. And we have data from Jerusalem with a particular field strength, and we have data from this gate, which are, and we can say that they were not not done at the same time based on field strength, because the field strength of this gate is significantly different than the destruction of Israel. So destruction of Jerusalem. So there's other ways that you can do this, using directional data or a time series of directions, and you compare it with a field model, and then you can date things. Does that answer your question?
Okay, I don't know. It depends on the students' response in the chat.
Oh, okay.
Yeah, but
right.
I think okay. I think we can move on and then
Come back to that. That's a very interesting topic.
Yeah.
And I find it very interesting. So anyway, here I yes, can I go on?
oh yeah, please go ahead. That was some nice.
We're almost done, and then we can chat. So the data in black are from the database, so other people's studies, and you can see here that, you know, really it does seem to be true that there is this hemispheric asymmetry where the northern hemisphere is stronger than the southern hemisphere. But I haven't tied it back yet to the field strength. So I'm going to the strength of the overall geodynamo. Here are all the data that I just showed you, only plotted against time. The blue dots are Antarctic data. They don't vary much through time. So this is the last Pleistocene data that we have. The green dots are from Iceland. The red ones are from Israel, and these cyan dots are from Hawaii. And you can see that they only go back 300,000 or 500,000 years. And so that's not good enough. And so we went back to Hawaii and sampled older. So this is this 1960 flow. There's a lot older rocks. They go back millions of years in Hawaii. This is where Honolulu is. And here's the big island that I talked about with all the active volcanoes. And we went and sampled all these other islands. And so now we have a better time series. This paper was just published by my graduate student, Brendan Seesh, who's now a postdoc in Liverpool. And here are his data. And this is for the last, these little triangles are the ones I showed you before. Here are our new data. And you can see that for the last million years or so, 1.5 million years, the field strength was stronger in Hawaii. And then prior to that, the field was weaker. And there's no asymmetry. When the field is weaker, according to these data, there's no asymmetry between northern and southern hemisphere data, because this is exactly the same answer as in Antarctica. So the northern and southern hemisphere data appear to be consistent with each other when the field strength is more like average. And so that is kind of cool, I thought. So here are the conclusions. The field was asymmetric, with the northern hemisphere stronger than the southern hemisphere over the last about 1.5 million years, maybe. Prior to 1.5 million, there's no evidence for a strong asymmetry, but the dipole was weaker. This is consistent with that prediction from the geodynamo models. But we need a lot more data, especially from the southern hemisphere. And we need to understand how this Bayesian method works and why, because we're using less than perfect samples to do this data collection now, and we need a much more sophisticated understanding of, and we're using micromagnetic modeling to do, and I'm hopeful that over the next year or two, we'll figure this out. And I just got funded to do a lot more work in the southern hemisphere. So I'm going to go to New Zealand and Patagonia and try to get more data from the southern hemisphere. And thank you. That's, I'm going to stop sharing now. And we can go to your questions.
Yeah, I think, Lisa, I think we're going to take a break, and then people are going to leave a question in the chat, and then we'll come back for, let's say, 10 minutes, okay? And it's also...
Hi, sweetie.
Say hello to Lisa.
Hello.
Hello. Hello. Yeah, now it's a break, and it's also feel free to bring baby into
I'm
this.
sorry if that was too long.
Yeah, well, it's okay. It's okay. Yeah, I thought that it would be split in 2 sessions, but it's okay to merge them as one together. That's totally okay. Okay. Yeah, we can take a break. So everyone, feel free to take a break or leave a question in the chat. Yeah, it's fine. We will come back in 10 minutes.
Okay, 10 minutes. All right.
Yeah.
Okay.
Yeah.
I'm still looking at your baby. You're muted.
Yeah. Okay, I will bring her stay for a couple more minutes. And hopefully, actually, Tanya is still working at home today in the morning. She also works by Zoom, maybe Huddle by Slack. I think she will pass by later on. So
Okay.
she is just awake, so she's not very burned now. She has just slept for an hour, right?
Okay.
All right, my friend.
See you.
See you
I'll
later.
be back in. Okay.
Yeah. See you in a couple of minutes. Hi, Lisa.
Hi.
Let's continue. And actually, Tanya is still working, so she's in another meeting. I cannot bring her here, although she's still at home, but that's okay. So there's another question. It's more general question. Is about that how you push for the research direction of the field, since you are leading the research direction in the geomagnetic field. So do you have any experience to share with those early career scientists? I mean, they are not, they are very early career. I mean, they haven't decided which direction they are going to, because most of them are undergraduate students. So there's a general question for that.
So where do I think that the field of paleomagnetism is going? Is that the question?
Yes, and how did you manage to direct the direction of the geomagnetic field over the decades, also including the past and the future?
Well, that assumes that I did. Does anybody listen to me? I don't know. The way to influence the direction of a field is to publish papers that are well researched, well written, and tell us an interesting story. So no matter what you're doing, you want to have some kind of a story that you're telling, you know, why are you doing this? And why do you think it's important? And then back up your conclusions with data as well as you can, and then and publish your papers so that the community can see what you're doing. Also going to, you know, things like AGU helps. So, you know, but the bottom line is writing the papers. And so finishing what you start, keeping at it until it's done. You know this, Johnny. Does that make sense?
Yeah, I agree.
So have
okay.
a good idea, have an idea, convince people that it's a good enough idea that you can pursue it, stick to it, and then finish it.
Okay. Next question is coming from me. I'm curious that for the study that you cited for that just published, I think this year or last year, on the new geomagnetic model, geodynamic model. So what's the new improvement they made on their technical end? Since in my interpretation that the viscosity is still many orders of magnitude off. So
wrong.
Yeah. So what improvement did they make so that they could make the patterns that looks real? I don't know.
This is not my field, and I've been skeptical of those models because of the orders and orders of magnitude difference between, you know, what the Earth does and what the models do. So they have a lot of models, and some of them are completely, you know, wrong. They just can't possibly be Earth-like. So they're trying to characterize the model outputs as being Earth-like or not. But the problem with that is that they assume they know what the Earth did. So why are they doing this? You know, so they look at the models. Do the models, for example, do they have reversals in them or not? Is the strength of the output consistent with what we think we know about the Earth? And so I think it's a very difficult field. But the improvements that are being made are that computers are getting all the time faster with bigger memories and more data. And so that helps, right? They can do little tiny pieces that are Earth-like and then try to extrapolate that. It's not my field, but I think maybe in 10 or 20 years, we'll have something that's more Earth-like in the parameters that they use. I'm not
Yeah,
sure
well,
that was.
yeah. From my perspective, that quantum computing could be applied in this field, then we will get very close to that, but we don't know how fast quantum computing could be achieved and be practiced in each specific discipline.
Yes,
And
you're right. Quantum computing could help. And I believe that quantum computers are getting better all the time too. My oldest son has a friend who does that. He works on quantum computers, and he told me that they were getting better all the time. But
another,
maybe decades, maybe a decade, we're within your lifetime. Quantum computers may actually be a thing.
yeah, I think especially for the most students here in the early 20s, I think in your lifetime, I think definitely you will, probably a lot of them, you have the opportunity to use them to solve your question, solve your problem. But what I see that in a much nearer future, what is practical in some other fields that's already happening is that, for example, by introducing deep learning, and then when you introduce a lot of GPUs, then could dramatically pump up the size of the system. For example, in molecular dynamics, the or first-principle calculation field, in some systems they used to only to calculate tens of atoms. Now in some systems they could calculate millions of atoms, and then still pushing forward to that. Although that's compared to the viscosity difference in terms of magnitude. I think the viscosity difference, magnitude difference compared to a realistic case is much larger than the geochemists that care about. I think because what do we measure in
magnitude, something like that.
Yeah, because geochemists now they could push for order of, let's say, 10 to the order of 5 to 20 to 10 to the order of 6 atoms, as well as how those are existed, then the equipment could measure them. So could push for really for a very low detection limit. So I think to me in geochemistry, the quantum chemistry modeling will merge with our micro analysis in a foreseeable future. Without quantum computing, people should have a high possibility of achieving that. The question is that what's the cost for that? So, but I believe that we are going to see several practices at least. People are going to achieve that.
Yeah, it's very exciting. The other thing is that I talked about, that we have to stick to the theory of magnetism. So that if you get larger grains than about 60, 70, 80 nanometers, they're not simple magnets. They're much more complicated. And to understand the physics of those things, we need computers. We need really big, really fast computers. And so that's the other piece of what I was working on, what is the physics of what we're trying to do. I mean, I made this empirical assumption. Why is that true? And is it true? And so for that, we need these bigger computers. And I think we're going to be able to do that without quantum computers. We just need to keep at it.
Well, I think this is I think it brings a very interesting case, even from my perspective, that when you go to nano scale, then a lot of the physicochemical properties change. For example, even the well-known phase diagrams we know actually is quite different than if this pushed in nanoscale than what people normally do experimentally. So that, I mean, for nanoscience, that's a whole nother field that even from the analytical and experimental perspective, there's still a lot of work that people could do nowadays. At least a lot of analytical instrument push for that. First, for example, atom probe that has been more and more widely used in the community nowadays. So, so I think for material science, that's also a very interesting field. We merge with the earth science nowadays.
Yeah, so we're living in exciting times.
Well, as always, I think each decade there's something that's exciting and hard. I mean, Okay, there's another question. It's a little bit more general. So they're very curious about your research, and they would like to know a little bit more about teaching. So could you introduce a little bit about the geology education? Geology education. Probably they refer to undergraduate education system. Is there anything that is very unique? For example, at Scripps.
Oh, our geology major right now is having a lot of problems, and probably you're doing, oh, isn't she cute? So I don't think we're doing very well at Scripps right now. Just don't quote me on that. But the departments that are doing really wonderful stuff are things like University of California, Santa Cruz. There's a number of departments around the country that are teaching earth science in innovative ways. I think Lamont Doherty Geological Observatory is doing a good job. So you can ask my opinion about particular departments, and I'll investigate it for you if you have specific questions. What I like to teach myself is a sense of curiosity, a sense of passion, and a sense of if you work hard, you will do something interesting and important. So those are hard to teach. I mean, it's not like you can have a syllabus and, lecture 1 is how do you be creative? That's not, you can't teach it. You can just encourage it. You know what I mean? I'm not answering your question, but I'm trying.
I think that's a very good answer, because you sort of disappoint them. I think that's good, because I think from my interpretation, that some students here, they would think that your undergraduate education is perfect. So when they hear you, that you're, well, I think speaking objective way, there are pros and cons. There are places that are doing better than the others. And also there are parts that are actually beyond what we actually teach in a classroom, specifically on textbooks. For example, that grit, the integrity, the perseverance. That's a very, very hard that's not a directly knowledge-based stuff that are very crucial for.
It's not, if you know these things, if you know these things, you will be fine. It's not that. It's that if you have an idea and you're willing to pursue it, and you're willing to work hard to figure it out and stick to it. And that's not something you can teach in a class. But it's how you succeeded, Johnny. Look at you.
Well, then I only have a question for this student, because you actually didn't tell us that what did you teach. I think in my knowledge that you not only taught geomagnetism at the Scripps, but you also taught the Python application. Could you talk a little more about the classes you taught?
Okay, I taught geophysics, field geology. I think how you do field work as one of my favorite things, because I like to be outside. And Python for science majors. I taught also, of course, paleomagnetism. And that class, the Python class, that's available online, and anybody can go and get it and download it and learn it, teach themselves. And my paleomagnetism book is also available freely online, and so anybody can read it. I also taught geophysics and basic earth science and lots of things. I spent 40 years teaching, so I taught a lot of different things. But more recently, I've been teaching the Python class and the paleomagnetism class and field methods. Those were fun. But I don't teach anymore. I'm retired.
So may I ask a little bit more about your Python teaching class? So how was your feeling? I mean, did you teach Python for 5 years in the last 5 years before your retirement?
Yeah, I think so.
So how was the experience? So how was the students' reaction to that course? So why some students were attracted to that? Because Python classes are still available at the UCSD main campus. I think in many departments they ran that for biomedical science, for example. I bet in computer science for sure. So when you read that class, was there anything special? That how was the students' reaction? I'm quite curious about that because I'm also, like I say, I use Python frequently now. I write Python for work. I apply machine learning by that. So yeah.
So I designed this class, the Python class, just using the examples. So say you want to teach how to calculate the best fit line through a data, right? So I pick examples from earth science. So my favorite straight line in earth science is the age of the universe, you know. And so I used those data from Hubble as an example for how to fit a best fit line. And then you show more data and it's not a line at all, right? So that's kind of interesting. But I designed the class, and at first, the students who took it were people who already knew how to program and were from the computer sciences department, and so they just wanted an easy grade. They wanted to take an easy class for them. But so then I stopped that by insisting that they have some earth science background. So they had to take our basic earth science class to get into my class. So these are just regular geology majors and grad students. And so they chose to take it because they really wanted to learn Python. And I was using examples that they could understand. And so it wasn't like, cell biology or something or something like DNA or something. And so I could teach like, how do you do deep learning with an earth science example? And so that was the philosophy. Also, there's no exams, and the students were allowed to pick anything for their final project, which they could write a program to do, but it was anything they were curious about or interested in. And so the final projects were just really cool. The students did all kinds of things. And so that was fun. So you guys should take a look at that class if you're interested in Python. And it's still expanding. So, of course, Python is changing itself all the time. And so every year I would have to update. So there was somebody who asked a question here.
Yeah, students are very curious about the helicopter. So would you share your experience? How did you get a helicopter? And some of more funny stories about it. I mean, students here are particularly curious about that. I think it's a bit hard for Chinese students doing geology field work here in China to get helicopters, but I think it's more common. Not that common, but still.
No, it's pretty rare because they're very, very, very expensive. So how I got the helicopter there was that I needed to I told the National Science Foundation that the secret to everything in paleomagnetism was down in Antarctica. So then, what was I going to do? So I wanted to sample a bunch of lava flows around an active volcano, the southernmost active volcano. Now in Antarctica, there's no roads. There's no way to get to those places, except for if you walk, if you take a snowmobile, or if you take a helicopter. So if you're going to work in Antarctica, anywhere away from just the base, you have to use a helicopter. And so the money for the Antarctic program includes money for helicopters. So having justified that I had to go to that place, then I justified having to use a helicopter to get to that place. And so they gave us the helicopter. So it's, it's a question of making the right argument. And I spent about 100 hours in a helicopter down there. But now if I wanted a helicopter, I couldn't get one. You don't. Here, if you can drive there, you're going to drive. Or walk there, you're going to walk. So
may I ask, the cost is like $1,000 an hour?
Yeah, at least. It must be more than that now. It's over $1,000 now.
Okay. But
so
okay.
It's just ridiculous amount of money, to spend going to collect. Yeah. But it's like, China just decided to go to the moon. Now that was not cheap, right? Right?
Yeah.
Went to the moon, and you got some rocks, and that was not cheap. And so the people who wanted to go to the moon had to make a justification to your science funding operation, the government, that it was very important that we go to the moon. And then once you've made that decision, then the money will follow, right?
Yes.
So it's all in your argument about how important something is.
Yeah, in my recollection, the Human Return Moon Landing project costs about $60 billion US.
Yeah.
But I don't know. I don't think that includes everything. So you'll probably only refer to human landing and return lunar mission. But I think from a planetary science perspective, it's also a good time, because there are a lot of parties that join the game, not only China, but also India, not only for the moon, but also for Mars, because China also has the funding and the plans to bring return samples from Mars. So I think
that's going to be really interesting.
Yeah.
So that compared to flying around in Antarctica is nothing compared to that.
Yeah, by cost, that's different. But anyway, having helicopters is very exciting to track students.
They're really fun. A lot of fun.
I once drove not helicopter, but the small airplanes that could take off from the lakes. Actually, that's what Minnesota.
Oh yeah.
Yeah. Those are more affordable, but it's still quite an interesting experience if I got to drive the plane. So that bar is much lower and much cheaper to rent. I drove it from one of my friends' plane. So that was a really fun experience. I bet driving a helicopter is much more interesting. I did that as a passenger at Hawaii, but I never drove a helicopter.
Well, I didn't drive the helicopter. That takes years of experience. I wouldn't even trust myself to, no, I didn't drive them. You have pilots who are extremely experienced, pilots who do that for you. They drive it, but you tell them where to go, and that's kind of fun. You should go, right over there, just land right on that spot right there, and then you go down there, and then you get out and you get your rocks and come back in. It's fun. Any other questions?
Yeah, any more questions?
I have lots of stories about the field. In fact, I'm writing a book called What Could Go Wrong, about all the things that go wrong in the field. They're funny little stories. So stay tuned.
Another question for a student. So what's the core spirit of doing scientific research? How to keep your passion with the research when it becomes your career? So rather than interest, once become your career, so soft, you keep that passion going on for decades.
Okay, so that's an interesting question. How do you keep that passion going? This is something that I'm interested in right now in my life because I've retired, right? So I don't get paid to do research anymore. And yet, I keep doing it, even now after, 45 years of doing this work. It's a difficult question because, you have other things that you'd like to do. Like if you have a family, you want to spend time with your kids. If you have a partner, you want to spend time with your partner. You want to spend time listening to music or reading books. I mean, everything takes our time, right? So where do you place your scientific interests in that whole spectrum of things that you could be spending your time on? But I find that it's the quality of the questions that you're asking that drive you. I've always just felt this deep interest in how things get magnetized. And I cannot give it up until I understand that. And I don't understand it yet. I've been doing it for, 50 years or something, 45 years. And I don't really understand how rocks get magnetized deeply, down to the atomic level. And so I just keep waking up in the morning going, geez, I wonder if I did that, I would understand it better. And, and so it keeps my interest alive. I don't know how long somebody else would, different people, everybody's different, and you have to make your own choices, how you want to spend your time. But just because you're getting paid to do something doesn't mean it doesn't have to be interesting. I mean, it can be interesting even if you're getting paid to do it. Does that answer your question?
Yeah, I think it's great to share your life experiences like that. Actually, I would bring an interesting, relevant story. I forgot what's the specific name, but that's what Mark Hirschman told me. It was like in his days when he was a student at Berkeley, there were professors, I think 1 or 2 professors in Berkeley who retired in their 60s and then still publish paper until their 90s. So in the end, they publish more publications after their retirement than before. Then the time they were at their position. So
yeah.
well, that's it. That's some extreme examples. But of course, they are motivated by what they're interested to do. It turns out after retirement, they don't have less probably administrative roles.
You don't have to teach anymore, and you don't have to be department chair or any of these other massively time-consuming tasks that to me are boring. I'm sorry. I just don't like managing committees and things like that. It's just not what turns me on. So being free from that, I've been able to spend a lot more time doing research, which is what I like to do.
Okay, Lisa, I'm going to check your records to see whether you will break that record in terms of the pre-retirement, after retirement publication ratios. I think everyone would have a ratio for that. You might break the record.
Well, I'm still writing a lot of papers, but I've always written a lot of papers. So I like writing. So I just submitted something 2 days ago. So we'll see.
Okay, I think we have kept Lisa for really long today, and it's great having Lisa sharing her research and her research experiences, teaching experiences, and her life experiences with us, particularly for a lot of undergraduate students who are still have a lot of room to choose a career, what you would like to be, which direction you want to go, whether you would like to be a scientist, and what kind of scientist you would like to be, what kind of lifestyle of life scientist you would like to be. So I think it's really rewarding. and refreshing to hear the perspective that I brought from Lisa talks. So let's thanks again for Lisa for giving us that talk. So everyone, if you could you turn your video on again to show your appreciation for our speaker today. And then we are going to turn the the meeting off in about 30 seconds or 1 minute. Okay, thank you again.
All right. Well, thank you for asking me. Okay, still a few more faces coming up. Yeah. Okay. More faces. Thank you for coming. And thank you, Johnny, for inviting me.
Yeah, I'm looking forward to seeing you in person. Probably.
Yeah, I'm planning on going to AGU, so maybe we'll catch up there.
Yeah, I also plan to spend 1 more week after AGU to Scripps.
Mhm.
Yeah, if you
Yeah,
happen
I'll
to
be
be there.
there.
Yeah.
I'll be
Yeah,
there.
let's see. Yeah, let's see whether we could meet up with that. But I mean,
You can't come for Thanksgiving. We're gonna have Thanksgiving.
that's too early for me. I still have a lot of responsibilities in November,
I
unfortunately.
remember when you came to my house for that one party. That was fun.
Yeah, that was a really fun experience. And particularly seeing people that are walking out for several rounds and continue the next meal. I mean, we should have more of that in China. I mean, in Spring Festival, we also have a lot of feasts for every family. I think we are lacking this walking experience. Yeah, and also it's great to fun to walk outside while meet your neighbors. Your neighbors also are doing exactly the same thing. So they were also working out for several rounds before they could continue the feast.
Yeah. Okay, well, I'll see you at AGU and maybe after we'll get together, have a long chat, catch up. Okay, bye-bye. Thank you for coming. Email me if you have any other questions.